Hey guys, welcome back. We're continuing on this standard of 2.1.1, looking at rock cycles, plate tectonics, volcanoes, and earthquakes. And today we're going to focus in on earthquakes and look at that as a bigger piece. All right, so many of you know what earthquakes are. They're natural vibrations of the ground. They're destructive. They kill people. They destroy cities. And anyone living in earthquake areas are there's potential dangers, and they're a way to minimize those dangers. So we're going to look through all of this today and really get a better understanding of earthquakes. All right. Most earthquakes occur when rocks fracture or break deep within the earth. And those fractures happen when there's stress, all right, and that stress exceeds the strength of the rock. So if we were to think about your leg, all right, and I started putting stress on it by trying to bend it, okay, all right, most of the time it'll hurt, but finally, when the stress exceeds the strength of your bone, what happens? Your bone breaks and it quickly snaps. All right. I know that sounds really terrible and painful, but that's essentially what is happening in the earth. And there are three types of stress that's happening in the earth. There's compression stress, so that's pushing it together. So that's like breaking a bone by crunching it up under something. There's tension, like pulling it apart. All right. And there's shear. All right. And that's a twisting sort of stress. All right. And when materials get deformed or warped by things in response to stress, this is called a strain. All right. All right, so what we have, faults, all right? Most earthquakes occur along fault lines, all right? And we talked about rocks fail when stress is too quickly or too great, all right? And it's a system of fractures, and the movement occurs and causes a fault. And there's three types of fault. There's a reverse fault, all right, and that's horizontal compression, all right? All right, and then a normal fault, which is caused by tension, and strike-slip fault was caused by shear. All right, so earthquake waves. So earthquake waves are a result of the vibration of the ground, causes what we call seismic waves. All right, and there's three types of seismic waves. First are primary waves, or P waves. All right, and these are the waves that cause the rock particles to move back and forth as it passes. Secondary waves, or S waves, all right, cause the particles to move at right angles to the direction of the wave. And surface waves cause rock particles to move both up and down and side to side. So our P waves are sort of like if you take a slinky and you were just to move your hand back and forth in front of you, sending waves along the slinky that way. An S wave is moving it up and down, all right, and surface waves just occur along the surface. So surface waves, of course, travel along the Earth's surface, all right, whereas P and S waves pass through the Earth's interior. All right, the first wave generated by a quake spread out from the point of the failure of the rocks. All right, and this point where this occurs is called the focus of the earthquake. And it's actually usually a couple kilometers below the surface. It's not on the surface. All right, and the point on the Earth's surface directly above the earthquake's focus is called the epicenter. So if we look at this image here, the focus is deep within the Earth, and if you go straight up from that, all right, that is called the epicenter. And then we have the fault line as it proceeds underground, and then we send up seismic waves from that focus and then up to the epicenter. All right, so how do we locate the focus, the epicenter of an earthquake? So that's really important. Like I remember it must have been 2011, there was an earthquake, and I was sitting in my office in the lab in Pittsburgh, and I remember sitting there looking at my coworker, and the ground felt like it was moving, and I was like, what was that? And we were feeling an earthquake that happened in Virginia. All right. So more than 90% of earthquakes you don't feel, and there's no damage. They just cause little itty-bitty shakes if you even see that. All right. However, the earthquakes we know about are, of course, the ones that are major and cause damage. All right, so how do we measure our earthquakes? Earthquakes are measured based on the amount of energy released, and it's called its magnitude, and it's measured using the Richter scale, all right, based on the size of the largest seismic waves measured, all right? It's a 10-fold scale, all right, meaning seismic waves in Earth on the of an 8 are 10 times larger than a 7. All right, so it's a logarithmic scale if you are familiar with logarithms. All right, and a magnitude 8 is 100 times larger than a magnitude 6. You can look at this lovely Richter scale here. All right, most seismologists use the moment magnitude scale. All right, and this is takes into account the size of the fault rupture, the amount of movement along the fault, and the fault rock stiffness. And it's based on the size of several types of seismic waves. Okay. The next way we can measure it is also by the modified Mercalli scale. All right, and that measures the amount of damage that we see. All right, and this is called the intensity of an earthquake, not the magnitude. This is called the intensity, is the Mercalli scale. All right, and you can look here on the side and look at what the different intensities, and it's 1 through 12 is your Mercalli scale. All right, and here's another image of showing the difference between the Mercalli and the Richter scale. So if you look, a level 1 of the Mercalli scale is a Richter 1 to 2, and a 2 on the Mercalli scale is a 3 on the Richter scale, and it just goes down from there, and the Richter scale ends at an 8, whereas it's a 12 on the Mercalli scale. All right. Another factor that determines a quake's intensity is its depth of the focus. All right, so how far down into the earth is this fracture occurring? All right, we could have a shallow, intermediate, or a deep. Deep focus results in smaller vibrations, okay, whereas the shallow focus results in larger vibrations at the epicenter. Remember, the epicenter is at the surface of the earth. All right. At a shallow focus, a magnitude 6 quake will have greater intensity than a deep focus magnitude 8 quake. So the deeper the focus, the less we feel on the surface. All right, so catastrophic quakes with high intensity are almost always shallow focus quakes. So those quakes that cause the most damage are generally shallow focus quakes. That means they're close to the surface. All right, so how do we locate an earthquake? All right, initially when the earthquake occurs, we don't know where the epicenter is, but it is determined using seismograms and travel time curves. All right, so we look at the waves determined by the seismograph, which measures the movement. All right, so first they find 3 seismic stations and they're plotted on a map. All right, a circle whose radius is equal to the epicentral distance is plotted, and then the point of intersection of these 3 circles is the epicenter. So if we look here, we had a seismograph in Portland, Salt Lake City, and Los Angeles. And then they took those and they determined the epicentral distance using the graph. All right, and then they made little circles that had the diameter equal to the epicentral distance, and where those 3 intersected in San Francisco, California, is where the earthquake's epicenter was. All right. Now, where did that epicentral distance come from? The exact arrival time of the P waves and S waves at a seismic station can be read using the seismogram. All right, and then we have what's called a travel time graph that can be used to determine by subtracting the travel time from the known arrival time. So if we know the arrival time of the P wave and the arrival time of the S wave, we can look at this graph, all right, and we can say, oh, the P waves arrived in at 5 minutes after, and we can look at these curves and determine the distance in kilometers or the distance in miles from the epicenter. All right. Seismologists have collected and plotted locations of epicenters, and these distribution of the epicenter reveals an interesting pattern. And we've discovered that most earthquakes are associated with tectonic plate boundaries, all right, with 80% occurring along the Circum-Pacific Belt, or the Ring of Fire, 15 occurring along the Mediterranean Asian Belt, and most of the remaining occur at ocean ridges. So if we look here and we look at where all these earthquakes are occurring, we can notice they're occurring along these tectonic plate boundaries. All right, so earthquake damage is a result of prolonged shaking of ground by the surface wave. So it's not the P or the S wave, it's the surface waves. And these can last longer than a minute. And many structures can't withstand this violent motion that's happening. So most of the damage results from collapsing buildings, and that causes most of the earthquake-related deaths. Now, the damage is related to the strength or quality of the structures involved, and most severe damage occurs to unreinforced buildings. If you want a lot less damage, then you look for wooden structures or steel frame buildings. Some buildings in earthquake-prone areas, such as earthquake, rest on large rubber structures that can absorb the vibrations made during a quake. So we can build things to withstand earthquakes. Buildings are destroyed as the ground beneath them shakes. In some cases, the ground floor fails, and this causes the upper floors to fall and collapse. And this is called pancaking. In other cases, the height of the building is related to structural failure. For example, in 1985, in the Mexico City earthquake, most buildings between 5 and 15 stories collapsed or were destroyed. And if they were shorter or taller, they only sustained minor damage. So there was that area between 5 and 15 stories that caused them to sway violently. Earthquakes can also cause land and soil failure. They can cause landslides. Soil liquefaction can cause houses to sink into the ground. And the earthquake waves can also be amplified as they travel through certain types of soil. Because soft materials have little resistance to deformation, so that type of soil amplifies the waves. And they're greatest in soft, unconsolidated sediments and in small and hard resistant rocks such as granite. All right, fault scarps are where the fault intersects the ground surface. So if we look at these images, you can notice where the ground has shifted, and those are called fault scarps. All right, another type of earthquake hazard is a tsunami, which is a large ocean wave. These happen generally when the earthquake occurs in the ocean, and they displace an entire column of water that's overlying the fault. The disturbance spreads out. In open ocean, the wave height is generally less than 1 meter, but in shallow water, the height can exceed 30 meters. They travel, the heights and the speed at which they travel make them dangerous threats to coastal cities. So this is image from the Southeast Asian tsunami. I would say just a few years back, but it was quite a while back now. All right, seismic risk. We've talked about how most earthquakes occur on areas called seismic belts. The past seismic activity is a reliable indicator of future earthquakes. Alaska, Hawaii, and some western states are at the highest seismic risk, and the central eastern states are at a risk as well. And these regions have all suffered earthquakes in the past and probably will again in the future. So how do we predict earthquakes? Seismologists are looking for this right now, and it's pretty much based on probability studies. And the probability of an earthquake occurring is based on two factors: whether there's a history of an earthquake in the area or the rate at which strain builds up in the rocks. Earthquake recurrence can indicate the fault involved ruptures repeatedly at regular intervals to generate similar quakes. So, for example, earthquake recurrence rate at Parkfield, California shows that a sequence of quakes of approximately a magnitude 6 shook that area every 22 years from 1857 to 1966. And this indicates a 90% probability that a major quake will occur in that area. Probability forecasts are based on the location of seismic gaps, sections which are sections of active faults that haven't experienced significant earthquakes for a long period. So if you live along a fault and it hasn't experienced an earthquake for a long period, you also are probably up for a chance of an earthquake soon. There is a seismic gap, for example, in the area that cuts through San Francisco. So there's about a 67% probability that San Francisco will experience an earthquake. Strain accumulation is the rate at which strain builds up, and two factors affect that. The strain accumulated in a particular fault increases earthquake probabilities and how much strain was released during the last quake. And another factor is how much time has passed since an earthquake has struck that section of a fault. It's relatively new, earthquake prediction. It's something that people are actively working on. And the ability to predict could help us prevent damage to property, reduce the number of injuries, and most importantly, to save lives.